Thanks, guys, for coming in person. Means a lot. I brought donuts for in-person people. So next year, attend in person, we'll get better food. The food will be the main event if we have more people in person. We'll cater something nice. Though we're in Washington, D.C., so some of you might have to make a trip out of it. But it would be a good excuse to see the White House and to see the beautiful fall weather that we have. All right, let's get started for today then. Welcome to day 3 of Qiskit Fall Fest here at the Catholic University of America. We are located in Washington, D.C. It's been a great 2 days of lectures, and today we're just gonna start coding with Qiskit and get started. We'll be following through some uh, notebooks provided by IBM, and we'll focus on a beginner notebook for the beginning of this session. Yeah, so on the agenda today, we'll be coding in Python on a Python notebook, some beginner tutorial exercises, and then later, Daniel C.R. Sosa will introduce the hackathon prompt that we will be hosting for the rest of this week. If you all missed yesterday when I mentioned this, um, IBM is hosting a closing ceremony for the Qiskit Fall Fest events. Qiskit Fall Fest is hosted globally, and there's over 150 universities hosting their own Qiskit Fall Fest. And IBM is going to be celebrating everyone's accomplishments on Tuesday, November 25th at 9 a.m. Eastern Time. This link, you can just register to attend the call, and it'll be a great time celebrating the end of this event. And welcome everyone that's joining. Okay, and then also, if you weren't here for the afternoon session yesterday and you would like to receive a participation certificate, please fill out this Google form with the name you would like to appear in the form and the email you would like it to be sent to. We really want you all to get some credit for using your free time and your very busy schedule to attend this event and better yourself by learning about quantum computing. It's a big pleasure to have you. So we would like to have something tangible to give you all so that you can remember your fun time here. I'll share these links in the chat in just a moment. Okay, and before we get into the coding for today, I have to extend one final thanks to IBM Quantum for allowing us to host this event at the Catholic University of America. And I would also like to thank our school and the Department of Engineering, Physics, and Computation for supporting us while we host this event. And I would also like to extend a big thanks to my lab members who are here today, who helped me book this room, who helped me set up, carry stuff, and approved my flyer colors. They were a big help. I would also like to thank my co-organizer, Dr. Daniel Sierra Sosa, for inviting me to help host this event. It's been a great experience, and I've learned so much about hosting an event. It's a lot more work than you think. Who knew like making these slide decks took so long? And then a final thanks to everyone who's been participating over the last 3 days. It's 3 days is a big time commitment, and it's really great that you all provided your support so that in the future we can continue hosting events like this. Okay. So I have some materials for you all today, but first let me share those links in the chat. Okay, I just shared some links in the chat. I have the one to register for closing ceremony with IBM, as well as the one to get your participation certificate. If you already submitted that yesterday, don't worry about doing it again. You're already taken care of. Just if anyone missed it yesterday, please fill that out. And lastly, I have a link to a
او
GitHub
اي
repository. Feel free to send your questions in the chat or raise your hand, and we'll be happy to take questions at any time. And the last link is a link to a GitHub repository where we're posting all of the lecture slides and materials that have been covered in the past 2 days, as well as our coding materials for today. Okay, so everyone, I would like you to please open that GitHub repository link, and we'll start there. Okay, so how we're going to be coding today is we're going to be uploading our notebooks to Google Colab. The reason why I chose to do this is that setting up, our local Python environments to get Qiskit running can sometimes just be a headache, and running it on the cloud just provides a lot of ease in the setup process. So hopefully all of you are running some code today. Okay. In this repository, we have all of the materials split up by days. To get to the notebooks for today, please go to the day 3 folder. Okay. Also, welcome everyone. 44 participants on the last day. I'm so happy to have you all here. That's great. We also have a great group of people in person. Okay, once you're in this day 3 folder, we are going to be working on the beginner notebook Qiskit fundamentals. So the best strategy of how to get this on Google Colab is to open this notebook in the GitHub and download raw file. And you're just going to download that locally. And then you're going to upload it to Google Colab. So that's the best way, in my opinion, to just get us set up for today. If anyone is having any issues or questions, we're having Jorge Savadera from yesterday who spoke, helping us in the chat and monitoring any questions that I might miss while I'm talking. Okay, so I'll give you guys a minute to download this notebook and then upload it to your Google Colab. Hey, Patrick, thanks for joining. Please take a donut.
Should I eat from?
Yeah, eat first, and then we can, if you want to do some coding, then we can set up. That's okay. You can just eat donuts and watch. All right. It'd be great if in the chat you guys could give me I'm in Google Colab and I'm ready to run some code. Yes, of course. Okay. On that GitHub repository, this is the main page. We'll be going into the day 3 folder and downloading the beginner notebook Qiskit fundamentals. It's a IPYNB, a Python notebook. And please open this and you can download it to your computer locally to then upload to Google Colab. And if no one's ever done that before, I might as well just do it here on this computer. So once you click that download raw file, you can see where you've downloaded this on your local device. I'll just put this file on the desktop so that it's easy for us to see. And then once you're in, and logged into Google Colab? Here, let me be helpful and share this for you. Yeah. Oh, thank you so much for the person who gave us instructions. We appreciate that so much. And all you need to get started on Colab is just a Google account. Yeah, thank you so much for those. Perfect instructions right there. Okay. If you've never been in Colab, you can upload that file by selecting Upload Notebook. Okay, I'm just going to move on. If anyone is having any issues at all, just getting in. Okay, great, you're in. Thanks for the update. Just please send in the chat and we'll help you out. So today I want to leave this portion of the event very hands-on because I think it's super important for you all to, struggle and get familiarized with the Qiskit Python library. Like any other Python library and packages, it's going to be a learning curve, just learning the syntax and what packages you have available for you and what's the best way to look at the documentation for it. So the best way of kind of getting into it is just starting at a lab like this, where you're just going to be doing some simple coding, but you'll cover a lot of rich material. A lot of my references that I have for coding Qiskit, I have gotten from other IBM Quantum events. My first IBM Quantum event was actually like a fall challenge in 2022, and I've just been kind of attending their events ever since because they're super organized in the way they provide material. It's really great. In this lab today, we'll be working through 18 core concepts. Each one has an exercise associated with them. You have two options to get started. You can either just get started in this lab and work through it without any external sources. If you are more familiar with Qiskit and you've already had some experience with it, that's a great way because every exercise is going to have a pretty detailed explanation of the concept, and then they're going to pretty much give you directions for what you're coding in the exercise. Yeah, as you can see here, this is the instructions. Read the explanation for each concept, complete the coding exercise in the designated cell, and then after attempting, you can check your answers in the solutions notebook. I'll post that after this session because I kind of want you guys to just see what you can do right now, and you can always check your work later. It's always important to run the installs and the imports before you run any of these cells. So do not forget to run this setup code block. It may take a minute, but luckily, since we're running on Colab, it's going to be less frustrating than trying to get this running on your own personal device. Okay, so don't forget to run that before we get started. So here is the example of the first exercise. As you can see, they have an explanation. Just read it very carefully, and they pretty much give you exactly what they're looking for. And then they lay out what they want for the exercise. And you can write your code here and run it. If you're looking at this and you've read it and you're like, I have no idea how to even get started, in our day 3 GitHub repository folder, I made a little text document with hints for how to get started with your code. So don't get overwhelmed if you've never coded with Qiskit. It can be hard to know how to do the basic setups, how to instantiate objects. So I provided some hints for everyone for the first 7 questions. And I think if you can get through these 7 questions today during our lab or whenever you have free time to go over it, you're going to be feeling a lot more confident in what coding in Qiskit really means. I think right now, unless anyone has any questions with the setup, I'm going to leave these 2 materials with you, and we will circle back in maybe 15 minutes and do a check-in and see how everyone's doing. I'll be on this chat the whole time if you have questions, but please utilize the hints if you're extremely lost, and the chat if you're like, they just threw me in with the sharks. We're here to help you, and we really want you to get some code running and make your own circuits today. So just let us know. For anyone who joined in the last, 5 minutes while I was explaining, we are currently in a GitHub repository that I shared in the chat. That's going to have your lab materials for the day under the day 3 folder. And we're all working in the beginner notebook. And what we've done is just downloaded that to our computers and then uploaded it to Google Colab. How's the temperature in the room? I have people in here who have coded with Qiskit before, I believe. I believe all of you had. Have you? Okay, so we have someone who's never coded before, so let's see if we can get him running some code today. The pressure is on you. I don't know about you, Patrick, but you can, you're sitting way far back, so we ignore you. And for everyone who's in and working on the notebook, let's give me a shout out when you've read through and you've either attempted question 1 or you've completed it. Maybe we can go through it together. Would you like to share, uh, copy and paste the matrix to the chat? Since we're doing, you know, it's weird, but you guys are doing a great job. That is the correct matrix. So let's go ahead and just run through this first problem together, and we'll talk about why we have this weird matrix and what this is actually coming from. Okay, so for this first question, we want to create a 3-qubit poly operator. So we want the gate Z, poly Z gate, to be applied to our third qubit. The order of which you should write out the gates when you're instantiating this poly operator is the 0 qubit is on the right hand side, and it's the, like, they call it the least, I forget what they call it, least significant or something, but the qubit 0 starts on the right. We kind of read it backwards. So if we want to apply a poly Z gate on our second qubit, that's the one that's going to come first. And then we have a Y and then a I. And I think it's great, before we look at what, sorry. Um, that's how you're going to print your, oops. Oh my gosh, I run a Mac and I'm on a Windows right now, and I keep pressing the Windows key as command. You guys live in a different world. Okay, so this is how you can print your operator, and then in order to get the matrix, you can use the method to matrix. Okay. Before we look at this 3-qubit matrix, let's just start by looking at a single poly identity operator for 1 qubit. And then maybe we can understand our matrices a little better. So remember that poly operators are going to be, they're going to have complex entries, and that's why we have this part here that might look weird. This is just because all of our poly operators are unitary and Hermitian matrices with complex entries. But for a really well-known matrix, the identity matrix, we're not going to have a complex part. So it's going to have a 0 coefficient on the complex entry. But this is what the matrix is going to look like for the identity operator, right? So it's good, like, if you're, wait, how can we print the matrix? So we can use the method toMatrix to print our matrix out. And then we can also just print out what the operator is representing by just printing what we've instantiated there. Okay, but now we're going to look at the example for 3 qubits that we're supposed to make here. And we get this matrix. If you got this matrix in the chat, let's celebrate. Let's go crazy. Okay, great. We have people with the correct matrix in the classroom. Um, so when we're creating, thanks guys, great work on this first problem. This is the solution of what you're looking for. Um, we're looking for a 8 by 8 matrix with complex and real entries to a represent applying 3 Pauli operators on 3 qubits. And the reason why this matrix is 8 by 8 is because when we are creating when we're applying gates to more than 1 qubit, and we imagine our circuit of, each of the 3 qubits has a gate applied to it, when we can actually visualize or understand those 3 gates as a combined unitary operator, but we have to perform a tensor multiplication between all 3 of the operators. And to get the dimensions of that, you're going to do, it's going to be 2 to the n number of qubits by 2 to the n number of qubits. That's going to be the dimensions of it. Oh, wow. If you're first getting into quantum computing, and you like to do math and you like linear algebra, I really enjoy trying to um, take quantum states that you've initialized and then just handwrite the gates that you've applied to them just based on their matrices. That is super fun to do, and it helps you understand some of the theory behind it of how we can represent these quantum gates operating on quantum states as uh, linear algebra. Okay, great job on the first question, guys. Ready for the second one, or should we wait? And if you just joined and you're in this notebook and you're kind of not sure where to start, in the same folder where the notebook was, I made a small hint sheet that can help you get through this code. Just so everyone knows, we'll have the solutions posted for this after um, today's session. I'm going to send you guys a big hint for the second question in the chat because taking time to read through documentation on the spot, I know that's a lot of pressure. Sorry, 1 second. Everyone in meeting. Okay, I just sent you the code to get a state vector from a quantum circuit and a pretty way to draw it. Are you guys on the third one? That one's a good question, I think.
There's a little bit of math to it.
Yes, yes. All right, thank you everyone who just joined. We're working on the beginner notebook with Qiskit fundamentals that can be accessed in um, our GitHub repository. The links are in the chat. If anyone needs help finding it, let me know. We'll go over the second question soon. All right. Okay, let's just talk about the second question now. The explanation, it gave us some basic single qubit gates that can impact our qubits, and some of them are specifically phase gates, such as the T gate, which adds a pi over 4 phase to the one component of a uh, quantum quantum state. So let's first just talk about, okay, how do we instantiate our first quantum circuit, and how can you do that um, by yourself, and kind of what's a setup like that? So normally we give a quantum circuit the alias of QC for quantum circuit, and this first positional parameter is going to represent the number of qubits that you want the circuit to have. Um, just to give you a little peek into the future, the second positional argument is going to correlate to how many classical register bits you want to have. But we'll get to that later. So one of the most important things that you can learn to do with your quantum circuit once you've instantiated it is learn how to draw it. And that way you can have a visual representation of what your circuit looks like. So, um, you know, especially when your circuit gets long or is very deep and wide, like you're going to want a visual representation to make sure you have all the components in place. And the way you can do that is by using the method draw on our quantum circuit. And we pass this argument to make the output pretty. we're just going to use matplotlib to make our quantum circuit look nice. So this is a quantum circuit that's empty. It has no gates applied to it with 3 qubits. When we instantiate a quantum circuit, all of the qubits are going to be in the 0 state until we manipulate them with gates. And the way that you can add gates to your quantum circuit, there is documentation for this, but in general, it's going to be the name of the gate and then the qubit that you want to apply it to. So now we can see that we've just added a NOT gate to our first qubit. And after we added this NOT gate, our qubit 1 will be in the 1 position instead of 0. Okay, now that we've done a quantum circuit together for the first time, let's talk about the solution to this second problem. Okay, we wanted to create a quantum circuit that contained 1 bit, which we know how to do, and we want to put that qubit in state 1, which we also know how to do. And then we're going to apply that phase gate that does this rotation, which we learned is the T gate from our explanation. And then lastly, we want to output this quantum circuit in Dirac notation using this state vector object. Okay, so when that's all said and done, we'll have a beautiful state vector that represents our quantum circuit here. Yes, exactly. Great job. How's everyone doing on the second question? All good? Okay, I really like this third question. It adds some math to this task, which you guys can figure out. But I think for anyone who's new to quantum computing, this question might sound a little tricky, but what we can do right now is go through what the state vector looks like for a single qubit in superposition. So this is not the solution to the problem, but this is what we can just cover as kind of a theoretical check. When we look at the state vector, let me draw this as well so that we have a visual representation. Okay, so when we have a singular qubit that starts in state 0 and we apply a Hadamard gate, what we're doing is we're putting it in superposition. Something that revolutionized quantum computing for me was beginning to think about superposition as probabilities that will end up in one state or the other. Okay? When we're writing the state vector for a single qubit, we're going to have 2 constants that are complex, that can be complex. They're known as amplitudes. And there's going to be an amplitude associated with each of the basis states of that qubit. You can think of those basis states as either being 0 or 1. And then furthermore, these amplitudes, when you take the complex square of them and add them together, it's going to equal 1. So the complex square of amplitudes is equal to 1, and an individual amplitude, when you take the square of it, you can kind of associate that with a probability of whether or not our measurement will collapse into either of the basis states. And once I started thinking about this as, kind of a series of probabilities, that helped me a lot visualize it in my mind. Because as we've talked about and seen over the past 3 days, a lot of this is non-intuitive on the first time around that you're seeing it. But once you get comfortable with seeing this state vector, and if a fun little math thing for you, if you take the square of these two like scalar values and sum them, should equal 1. Okay, and for this specific problem, let me get the solution pulled up. Meet everyone. So for this specific problem, we want to create a quantum circuit that has a specific probability to measure the 1 and the 0 state encoded into it. And we can, instead of using the Hadamard gate, which is just going to give us, a 50-50 probability to be in 0, 1, we can use a RY gate to encode a custom rotation angle, which we can also think of as a probability. I'm going to send this IBM answer in the chat, but we'll talk about the math first. Okay, so in the description, it gives us a hint that we can use this right here. We can kind of work backwards with this description of superposition to find the angle we want to encode our rotation gates with by taking this coefficient to the state vector and getting the square of that. Okay, so in this example, we are focused on trying to get our qubit in a superposition where the probability of measuring 0 is approximately 14%, and the probability of measuring 1 is 85.4%. I shared the hint here in these notes that we know that we want to solve this pretty much. So what we're going to have to do to solve this in order to get our angle of theta, which we'll use in our RY gate to actually encode the superposition, we're first going to have to take the square root of that 85%, right? And then we're going to have to apply the inverse of sine to both sides and then multiply everything by 2. And then that will get us our rotation angle. So I'm going to send you in chat the method I use to solve for this probability using NumPy. So that now you should have the angle theta, and you'll just need to apply this in an RY gate. If anyone has any questions on this, this kind of problem is one of my favorites because we're getting that multidisciplinary nature of quantum computing where you're going to have to think about statistics and math while you're constructing your circuits. And in small problems like this, we can do it by hand and we can come up with solutions by hand. And that's what makes solving these problems really fun. Okay. So let me go ahead and just type out this answer. Gonna get the chat. I gotta steal this. Okay, so after we calculate this value for theta, we're going to make our quantum circuit with 1 qubit, and then we want to apply our Y gate with theta, and we're applying that to qubit 0. And then afterwards, we want to visualize this circuit that we made on our block sphere, which I will also share in chat how we can do that. Okay, cool. Okay, so after we did those calculations for theta, we're able to encode this as a superposition on a qubit, and then we were able to visualize it with the block sphere, which shows us where our state vector exists on the block sphere, and kind of, if you've never seen a block sphere before, when the arrow is pointing to where our state vector lives and exists. When it's pointing up, that means that we are in the state 0. When it's pointing down, we are in state 1. And when we think about applying a Hadamard gate, which gets us an 50-50 possibility of getting either a 1 or a 0, think about us living on the block sphere directly at that center point. Okay, but in our example, we wanted an 85% chance that we'll end up measuring a state 1. And that's why our arrow here is pointing more towards state 1. Yeah, state vector, visualizing it on the block sphere is great because you can just think about that arrow collapsing to either side of the block sphere whenever we perform measurement. Okay, what time is it? How's everyone doing? Are you having fun coding with Qiskit for the first time? There's 18 problems in here. I set you up with hints for 7 of them. I want to I want you all to have more time to work on this and really read through the problems and the explanations because they're great resources. And also they're great at familiarizing you with Qiskit documentation and just like how do I Google search how to do things in quantum computing, just like when you're learning any other Python package. So that's what these exercises are great for. And also you'll have this somewhere as a reference in case you're like, okay, how do I get a qubit in superposition, and how do I create a entangled state between 2 qubits? It all exists in this beginner notebook. I really hope that you take the time to go through it. And after this, I will post the solutions so that you have them. But if you have more questions on these notebooks, feel free to reach out. And don't get discouraged if you're doing this for the first time and you're having issues. If you're having issues kind of getting started, this is going to be a completely different language of computation that you have to see multiple times before you feel confident, just typing all of these things from memory. Okay, and we're about to get to presenting our hackathon prompt, but today we just looked at a beginner notebook. IBM provided us with a intermediate level notebook as well that I have also posted on that day 3 folder. It is called Intermediate Notebook. The I'm gonna mess this up, the DiVincenzo criteria. So what this is it is a list of criteria that defines a quantum computer, and we run through examples that demonstrates how using our Qiskit application we meet all of these criteria. If you were enjoying what we did today and you want more and it's guided work because you'll have a solution afterwards, please check out this intermediate notebook. These things are great to kind of just get your quantum muscles flexing to get ready for more complex algorithms and projects on top of this. So yeah, please check out both these notebooks. After the session, I will post the solutions for them. But I encourage you to just try to do it by yourself at first. And the questions are more challenging than you think. Even though this is beginner, it's going to take some time for you to just get familiar with the concepts. Okay, great. And if you haven't seen it already, on this main page of the GitHub repository, we've posted lectures from the last 2 days of Qiskit Fall Fest. And we also have some event photos and these labs. We also linked on this a link to a YouTube playlist where if you missed any of the sessions and you want to check them out, we did post them here, so you can watch them. Also, we just have this as a reference for good memory, and we hope that we can do this again next year with you all. Okay. Now I'm going to hand over this presentation to Dr. Daniel C.R. Sosa, and he's going to give us an outline of what our hackathon prompt is. This hackathon, once it's live, we'll try to get submissions by this Friday at midnight Eastern Standard Time. Okay, I'll hand it over to him now. Do you want to share your screen from there?
Yeah.
And also thank you for the lovely comments. We really appreciate you all being here.
All right, so I think I'll mute myself. All right, so
Sorry, let me mute myself.
one second. Let's kind of the volume. Okay. Oh, nope.
Oh, no.
Please turn off the classroom speakers. Just one second. I think we're good.
Yes.
Yeah, I think we're good. All right. So for this hackathon, what we are going to do is we are going to try to solve the battleship game proposed by Basque. This is an organization of quantum computing in the Basque Country in Spain, and they have a really, really good portfolio of quantum services, and they propose this beautiful game that we are going to try to solve in this hackathon. So the idea on this particular problem is that we are going to try to emulate a simple game of battleship, where basically what we are going to have is a board where we are going to have rows and columns. Namely, for the real game, we are going to have 10 rows and 10 columns. And then we are going to have those rows and columns labeled by letters and numbers, and we are going to place our boats inside those positions, right? So when we are when we are playing the game, one player is going to call one row and one column, for example, B7, and then the other player is going to say if it hit the boat or not, right? So for this problem, we are going to change a little bit the rules. But at the end of the day, if we have a boat or if we have a bomb, it's going to be identical. So what we want to do with this game is find all the ships with the minimum chance of hitting them. So we are going to base this game into the Elite Survivement Interaction Free Bomb Tester, where we are going to emulate in a quantum computer a Mach-Zehnder interferometer. So the idea, or the basic idea between this type of schema, is that we are going to create in the quantum computer a Mach-Zehnder interferometer. So in the Mach-Zehnder, we are going to have one light source that is going to send just one photon, and that photon is going to basically go over a set of optical elements. First, we are going to have one beam splitter that is going to divide 50% the chance of the photon to pass through or to be reflected. And then we are going to have a full mirror that is going to reflect that photon. So basically what happens with that photon when it goes here is going to be split into 50% chance of being reflected, 50% chance of being transmitted by the beam splitter that we are having. So once we do that, basically what is going to happen is that this other beam splitter that we have upstairs here is going to actually send this photon either to a detector that we are going to have on this side or a detector that we are going to have on this side. So basically what we are playing here with is the superposition of the states of this electron that is passing this Mach-Zehnder interferometer. And this is going to be our device for doing the experimentation. We are going to then add a bomb on one of the arms of the Mach-Zehnder interferometer. These bombs, we are going to have two possibilities for them. One is that the bomb is actually live, and if it gets hit by the photon, is going to explode. But you could also have a dot. The dot is going to be a bomb that is not going to do anything and is going to allow the photon to freely pass over it, and you're going to be able to understand that nothing happens. So as you can expect, one of several things are going to happen. First, let's say that the photon is going to take with 50% chance this arm of the Mach-Zehnder interferometer not hitting the bomb, either dot or bomb, right? The other possibility that you're going to have is that you're going to have 50% chance of the photon taking this pad, and then you're going to have two types of situations here. One, the bomb is going to explode, or the bomb is going to be a dot and is not going to explode. But basically, what happens is that as we are creating this type of black box that is the Mach-Zehnder interferometer, we are going to be playing with the with a strategy that looks like the Schrodinger cat, where the bomb is going to explode and not explode at the same time, which is actually quite interesting. So being that the situation, what we will need to do is we'll need to place the bomb in one of the arms of the Mach-Zehnder interferometer and study what happens. And then what we will need to assess here is that there exists a chance of detecting this bomb without hitting it. Why? Because basically what we are going to have inside this Mach-Zehnder interferometer is the superposition of all the possible paths that the photon is going to take. Remember that the laser that you have there is going to emit a single photon for each of the experiments that you're going to have, and you're going to have the possibility of taking the arm with no bomb, having the possibility of taking the arm with bomb but it's a dot, and having the possibility of taking the arm of the bomb but the bomb is live and could explode. So when you have the empty Mach-Zehnder, basically you're going to say